Hello and welcome. My name is Chad Teets, Field Application Engineering Manager. I would like to introduce you to Rahul Premkumar, Enritsu Field Application Engineer. In this video, Rahul will demonstrate Enritsu's 5G NSA RF test measurement solution for testing FR2 millimeter wave devices. Thank you again for choosing Enritsu Test Solutions.
Okay, cool. So so in terms of the system components, again, it's not a single box solution. As you know, there's like a lot of components involved in this system. So the first thing is our Mx800010A call box that can do sub-6 and millimeter wave for both signaling and non-signaling. And we have 8821C, our LTE anchor for 5G non-standalone mode. In terms of up converters, we have 28 gig, which is the 1A. And we have the 39 gig, which is the 2A, and we have a third type of converter that supports both bands from 24.25 to 43.5 on a single system. So that is something like we don't have it yet, but it's commercially available. Okay. In terms of shield boxes, we have our MA8161A that is typically used for both FR1 and FR2. Again, it's mainly used for a simple connection, call verification, and for doing basic throughput performance measurements. All right. In terms of 5G DUT for our demo today, for FR1, I have OnePlus 770 Pro McLaren device that supports multiple combinations of TDD and FTD. And for FR2, we have Samsung Note 10 Plus device that can do band 260 and band N261. All right. Mm-hmm. So in terms of physical setup, this is how it's going to look. I have my LTE anchor on the left, 8821C. 8000A is my 5G call box, and I have my RF converter. So, and then the output of RF converters goes to a combiner where I combine the signals from the LTE call box and the 5G call box, and then feed it into a shield box or a chamber. All right. So in terms of the RF converter settings, we have port 1 and port 2. So port 1 is for phi measurements and port 2 is for theta measurements. So if you want to do SISO dual polarized measurements, then you can use one converter. If you want to do 2x2 MIMO dual polarized, then you'll use like two different converters. All right. And then in terms of control and sync cables, of course, like since this is still the NSA's non-standalone mode is still based on LTE backhaul network and protocol, so we would still need the LTE base to which the device initially attaches to, and then add your NR cell. So for that, you would need time sync, clock sync, and frame sync, and this is especially required when you're trying to do TDD testing, especially for a millimeter wave, because it's all TDD bands right now. And on the sub-6 side, we do have like a bunch of TDD frequency bands like N41. So for those scenarios, for testing those frequency bands, you would need the sync cables properly configured. All right. So
can I have a question on the previous slide? So the phi and theta. So in this case, is it like just outputting the signal on both polarization? But phi and theta is polarization, right?
Yeah, that's right. But if you want to do a single polarized antenna testing, then it's enough if you do just phi. If you want to do both, then you'll probably need to have like two connections.
So in this case, the same signal is essentially.
Yeah, that's correct. Yes,
got
that's right.
Got it.
Yeah.
Okay.
Sorry, there was some other question.
I wanted to go back to that diagram as well, where Jang-Il had the question. And it basically goes to Jang-Il. So we would connect the dual polarized antennas to the phi and theta, or to the port 1 and port 2. So
for us, we will need two converters because we have two streams for the two phi and theta.
So I mean, when you say two streams, it's for MIMO or just like two independent streams? Okay, that's MIMO. So so then you would need two RF converters then.
But do we really need the phase shifting between them, or could we theoretically treat them as two single ones?
You actually don't need that. If you're not doing beamforming kind of testing, then I think just a single polarization measurements should be good enough for you.
So for us, we have a geopolarized antenna, so I think it has to be a single polarization from the unnative side.
Okay. So then, I think you'll need two converters then.
Okay.
Yeah. Okay. All right. So, So again, as I said, this is my control and sync cable connections. So my sync output, which is my time sync and clock sync, from the MT8000A 5G call box needs to be synced into the 8821C while adding your secondary cell group, which is my NR frequency band. All right. In terms of control, so again, 8821C has been there for the market for a very long time. So it's a pretty stable product, and it has an inbuilt Windows 10 or Windows 7 OS. But still, like since MT8000 it's still in the early stages of the GUI development. So the box needs to be controlled by a standalone GUI installed on a separate PC. So this PC will control both the call boxes on the same software and the same GUI. I think that is a good thing, making like the control of everything, the entire setup in a single standalone GUI. So, so this is a setup that I have.
What is this? Sorry, I'm slowing down. What is this MN8110B? Is it the big equipment or is it just an adapter?
That was an external I/O a connector. Again, it's not required right now because we have a cable that can do it. So this was an older box. Right.
Got it.
Yeah. So
thank you.
Yeah. All right. So this is a setup I have. I'm sorry I couldn't do a video kind of thing, but again, this is just the photo of the setup for FR2 that we have in the office right now. So on your left, that's my 8821C, and you already see it's in NSA mode. And in the middle, it's my MT8000A. And the bottom, you see like there's almost 4 cables coming out, right? So the slot 1, again, I think we've actually been through this, but I'll again probably explain this in detail. So we have like 6 different slots in MT8000A. Slots 1 and 2 are for...
Yep.
Sorry?
No, I think my joint,
okay.
Maybe.
Okay. All right. So the slots 1 and 2 from the bottom, that's slot 1 and slot 2. These two are used for RF cards, like where you can generate FR1 and FR2 signal. Slots 3 and 4 are typically used for baseband signal processing. If you want to do like higher level layer testing for like scheduling and DCA kind of thing, you would require these 2 baseband slots. Slot 5 is for a data transfer module. If you want to do application throughput testing, like IP layer throughputs, then you would have to install the DTM module, that is the data transfer module on slot 5. And then slot 6 is typically used to control the hardware from the PC, and also it has an application port where you will be sending in all those IP data traffic. Okay, so these are the 6 different slots, and I'll probably go into detail about slots 1 and 2 because this is where we'll be configuring our RF connections here. So slot 1 has 2 TRX modules, TRX1. So this is TRX1 and this is TRX2. Each TRX modules has support for both FR2 and FR1. For FR1, we have one main port, which is full duplex. You can do downlink and uplink, and one aux port, which is uplink only. Okay, so you have one main and one aux for sub-6, and you have one FR2 port for generating one FR2 signal. So each TRX modules can have 2 RF ports for sub-6 and one RF port for millimeter wave. All right, so each slot has 2 TRX ports, so just double the number of RF ports. So in total, if you have 2 slots, you can do up to 8x8 MIMO for sub-6, and you can do 4x4 MIMO for FR2 millimeter wave. Okay.
And FR2 ports are full duplex as well?
Yeah, FR2 ports are full duplex. Yes. So you see,
is the minimum configuration 2 of these modules? Or
the
can
minimum,
I use a 2x2 MIMO with only one?
You can use 2x2 MIMO with one for FR2. Yeah, you can do that.
Okay.
Yeah. And again, it's really flexible. It's modular, right? If you don't need any RF card on slot 2, then you won't need to buy that.
Mm-hmm.
So, okay. Okay, and then so if you look at the cabling connections, you see 2 cables coming out of the slot 1 TRX1 port for FR2. So the black cable, that is my control cable for the up converters. Okay, so if you want to switch between phi and theta, this cable will be used by the MT8000A hardware and the software to actually switch between different polarization or talk to or generate the signals on both the polarization. So that cable is typically used for controlling the up converters. Okay. The second cable is your RF cable, the one with the yellow color. So that will actually feed your IF signal from the MT8000. So the MT8000 can generate either RF or IF signal. Okay, when I say RF, it's 0.4 to 6 gig, and when I say IF, it's from 3 to 12 gig. Okay, so based on like whatever frequency that the device can handle, so the MT8000A will generate the IF signal from 3 to 12, and then this LO cable will carry that signal and feed that into my up converters. Okay, so this up converter will actually then convert my IF into millimeter wave to 28 gig or 39 gig, and then you feed that into my shield box here. So that is the main purpose of having these up converters.
So let me check whether I understood that. So one is the LO cable, and the other one has the baseband, or we call it IF signal, and the TX-RX sync. So it has control signals as well, correct?
Yeah, that's right.
But the LO is a pure LO.
Pure RF, yes, yeah.
Pure RF, yeah, sorry.
Yep. Yep.
Okay.
Okay.
And for this, it seems like you're doing 2x2 in this.
No, I'm not. So what I'm doing is I have a 39 gig signal coming out from slot 1 TRX1, and I have a 28 gig signal coming out of slot 2 TRX1.
Got it.
So the reason being is I still don't have a multi-band converter which can do both frequency bands at the same time. So that's why I'm using two different RF converters for doing one for 28 gig and one for 39 gig.
Got it.
Okay. And the other thing, just to keep in mind, is most of the commercial devices out in the market, as far as I know, for FR2, I think SISO is only supported, but we might have 2x2 MIMO on S20 devices that just came out.
Got it.
Okay. All right. Okay, so this is how the setup looks like. Any questions on the setup?
Yeah, I have one question for the remaining slots on the center device. So there are two empty slots. What is the third from the top?
Third from the top. So that's my baseband slot. So this is a compulsory slot. If you have an RF card that you have installed, then you would obviously need a baseband processing module.
Okay, so that's basically generating the baseband and up converting it to IF.
Yeah, that's right.
Okay, but the slots on top and bottom of that module are empty.
It's not required. So that is for higher capacity. So if you're looking to test an FR2 signal with 800 megahertz bandwidth, then you would need two baseband slots.
Oh, okay.
Right.
Then for 400 megahertz, which is for our
single module is enough. Yeah.
So for us, it'll be one of the two baseband and one of the two RF.
RF, yeah, that's right.
And the top we anyhow need because it has the sync communication, the 10 megahertz.
Yeah, that's by default. Yeah, that's by default. You don't have to do anything. So the slot 5 is typically used for data transfer. Again, as I said, if you don't worry about like doing higher level throughput testing, then you don't have to have that DTM module card. You can just do your Mac throughput testing, which also could help you define the performance of those devices. So that should be fine for you.
So maybe it's a question for later. So what we're trying to do is connect to like you have the Samsung handset and measure throughput. For that, do I need the IP layer throughput?
No.
Or do I need the MAC layer?
Just the MAC layer PDU should be good enough for you.
I see.
Yes. Yeah. Okay.
Great. That's great. So we won't need the 5, 3, and 5.
Yeah, that's right. Yes. The other thing is, I'm not sure like what type of test scenarios you're also looking to test. Like, I don't know if you have any kind of multipath or fading involved in your test plan?
I don't think so. So it's mainly because mainly for testing our repeater. So
Right.
there will be this device and the handset on the other side.
Okay.
And we're gonna introduce repeater and show the difference. So that's the main purpose.
So it's basically a line of sight kind of signal then.
Yeah, it's a line of sight with the
that's
path loss control.
Right. Okay. So then, yeah, I think you won't need that. So just saying. So as I said, right. So right now I have the baseband card on slot 4. So slot 3 is empty. So if you want to add fading to that, then you can do that on slot 3. So the slot 3 is capable of generating the fading profiles defined by 3GPP for FR1 and FR2.
Mm-hmm.
All right.
And is there any limitation if we need more than 2 TX-RX modules that we cannot use them due to power supply limitations, or can we put theoretically 4 of these modules plus 1 reference clock module plus that 1 communication module? Could we also fit that in?
There is no limitation, but the one thing is, I mean, if you buy just one RF card now, and then in the future, if you want to add more, then you can do that. And then you can also add the baseband processing for that accordingly. But there is no limitation per se for that. But I don't know what your question was.
I'm looking at what are the hardware limitations we might stumble over in the future, because when we switch over to that measurement system, we know that the standard will evolve further. Who knows? Might become a 4x4 FR2, and then I want us to not be stuck per se having to buy a new case, new module case, and not knowing whether that can be truly all concatenated to higher MIMO order or whatever have you.
Right.
For example, I think the RF card, if we just do 28 gigahertz, for example, then we can do 4x4
with two RF cards. Yeah.
Yeah, with 2 RF cards and 1 baseband card for 400 megahertz.
Right.
If we want to go to 800 megahertz 4x4, then
it's already
right. That's right. And if you want to go beyond that, so because we already tested this at Qualcomm, so we are doing like again, this is for sub-6, so we're doing 8x8 2CA, and again, this is all just 1 CA, right? It's only SISO 1 CA. But if you're doing like multiple CA combinations for FR1 and FR2, there's not much defined for FR2 and 3GPP right now, but for FR2 we have done like up to 3CA 4x4 and 2CA 8x2 using two Mx8000 call boxes. So again, there is room for additional flexibility if you want to like go beyond whatever your current limitation is. So that is something we've already covered that with the chipset company. So yeah. Okay.
Thank you.
Problem. Cool. So okay. So again, this is what we just went through it. So the different slot information and the RF cards and the baseband slots. So if you look at the RF sub modules here, as I said, for sub 6, we have a separate card that goes from all the way below to 400 megahertz to 6 gigahertz, and then we have a separate module for IF, which is 3 to 12 gigahertz, and this is specifically used for millimeter wave alone. And then we have an extended card. Again, this frequency band is not used by most of the customers, but this is an extra option that if you want to test that particular frequency bands. Okay. Again, this is what we just went through, a different slot information. Okay, so just a front and back panel of our a millimeter wave converter. So as I said, like my port 1, that's for phi, and port 2 is for theta, and this is my input and output levels. And that black cable that controls the converters is this one, and this is my RF cable connection for IF to millimeter wave conversion. Okay, and these connectors that actually comes out of these up converters are K-type, and we have a special cable that actually goes from K to an N-type or an SMA connector. Okay, again, this is made by Andritsu. Okay. Yeah, so these are all the different converter specs we have today. So the 1A is 28 gig, 2A 39, and the thing I was talking about was 3A. So if you're looking at test like the entire millimeter wave frequency range, then this multi-band RF converter would be the best option for you. So the only thing that changes between the multi-band and independent converters is the output level. So you just have a little bit of dynamic range when it comes to output level in terms of the multi-band, because you can go beyond like plus 5 dBm. So you have a 10 dB of like range for the maximum output level. So, okay. So you guys mentioned like you were looking to test primarily on 28 gig. Is that right?
Yeah. That's the first step, but I mean, we do look both at the 24 gig. We do look at 37 gig. So that's something we need to decide.
Okay, got it.
But the first one, Jang-il, covers both the 24 and the 28.
Yeah, so first one is missing 37, which may be fine.
But you don't have to go beyond 43, right? I mean, because the max we can go is 43.5. And I think we are also working on a different converters that can go up to 70 gig. Again, that's for a different test case. But if you are looking at 2A only, it goes only till 40 gig. So if you have like a new frequency bands that can go up to 43.5, then you might be looking at the 3A option.
I think mainly number one should be fine, but it depends on the price sheet, I think.
Right, that's right. Okay, yeah, so in terms of the frequency band supported by 3GPP, so N260 is 37 to 40, and then we have N261. So these two are the most commonly used frequency bands commercially today by Verizon, AT&T, and T-Mobile. And the other frequency bands, I've seen it, but I don't know, most of the devices don't support it today. So for our demo, I'll be using N260 and N261. Again, this is the shield box. So this is what I was talking about, just a basic shielded enclosure box that can support both sub-6 and a millimeter wave. So the front 8 ports you see here, so these are all the RF ports for sub-6, and we have another 8 RF ports at the back that can support up to 40 gig frequency. So you have like 8 for sub-6 and 8 for millimeter wave. Okay, this is just a high-level overview of like what the shield box can do. It's typically used for just the basic call connection, a verification kind of testing, do a basic throughput. If you want to debug a device, like what happened, what call failure or a handover failure kind of thing, then you can use this. The main thing is the antenna type. So we have like 8 antennas inside for millimeter wave, 4 for 28 gig, and 4 for 39 gig, and each of these is in a spiral antenna mode. Okay, so this is how it looks like inside the shield box. So you see the spiral antennas, like we have 8 of them. So the 4 antennas that's labeled in white, those supports up to 28 gig, and the other one, which is non-labeled, it supports up to 39 gig. Okay, and these patch antennas, it's for LTE connections. So you have both LTE and millimeter wave inside this shield box here, and this is how you place the device. Which is so this foam is placed on top of this antenna setup, and then you have the device on top of that. So it's kind of a radiated near field measurement, right? It's not purely OTA or it's not purely conductor. It's closer to your antenna locations.
Correct.
Okay. Okay. The last thing is this LT anchor. So again, this is something we already went through. So now I think I'll show you the system. Okay. Let me see if you guys can see the full screen mode. Does it look good?
Yep.
Okay. All right. Sounds good. Okay. So in terms of the software, so this is what we typically use. So it's called Mx800010A Application Launcher. So once you click on it, it's going to throw you a different system slot information and my firmware downloader. If you want to upgrade the hardware or the latest firmware according to Qualcomm builds and I don't know, by different chipset builds, then you can use this option to install the latest firmware. An option installer is typically used to install any new licenses. If you're buying them or like trying to loan them, then we can install it here. And my system configuration will show you the entire hardware and software information of this MT8000 box. So here we have two test interface. One is slot 1, slot 2. If you go to test interface, I have two options, RF converter and RF 12 gig. So my slot 1 is configured for supporting IF from 3 to 12. And then it also can support RF converter. Okay, but when I go to slot 2, it supports RF 6 gig, which is 0.4 to 6 gig, and then it can also do RF converter. It depends on how you license the hardware side. So based on that, you can select which option you want to test and which frequency range you want to test. All right. And once you select the test interface, the next thing is you want to select if it's main or aux. For converter, it doesn't matter. There's only main. There is no aux. But for sub 6 and IF, you have main and aux ports, so you can switch between these two. All right. The same thing for TRX2 and the same thing for slot 2 TRX.
Good.
All right. Okay. And then on the right hand side, you see all these firmware informations, right? So all these different versions, whatever you see, it's really based on like the handset manufacturer guys and the chipset guys. So if you look at Qualcomm keeps changing the parameters like on a weekly basis for different handset manufacturers. So based on that, Android also needs to update their hardware because the 5G call box needs to be aligned with the chipset manufacturing guys. So these different firmwares are for different handset manufacturing guys. So I'll use system number 1 for like, I don't know, for LG, and then system 2 for Samsung. So that's the reason we have like the capability of installing firmwares up to like 10 different systems. So you can switch between these 10 different systems for testing different handsets. Okay, so you have that option. And then these are all just the hardware information. Again, as I said, like slot 1, 2, 3, 4, and 5, 6. What is installed? What kind of licenses do we have? Again, CA, SISO, MIMO. Again, this is a fully loaded box, so you have everything. All right. Okay. All right. So let's open up the actual software. So you click on System 1. That is the latest Mx800010A, which is my RF measurement software. So once you open that, the first window that you'll see is my LTE window. So this typically controls my MT8821C, the LTE anchor. And the second window that you'll see is my 5G NR window, which supports my MT8000A. So this window was typically based on the same software development team that created the GUI for the MT8821C. So we use the same strategy and the concept to actually create the same GUI for 5G NR. So these two are the same right now, but the good thing is a single software can control both the hardware right now. Okay. So in terms of configuration, again, there's like tons of parameters that you would configure for LTE and for NR. So the first step is configuring my LTE signal here. Okay. So what I do, like, I just select my frequency, is it FTD or TDD, and select the band 2. And once I'm done with that, then I set my level. So this is my input level. Basically, this is based on the UE's feedback power or transmit power. But initially, we just set to a minimum level where the UE can actually receive the signal transmitted by the LTE call box and then decode it. All right. And then this is my output level. This is my RSSI typically, and this is my E3. Okay, and then in terms of external loss, and this is sub 6, there is not much loss, so I've added only 5 dB of loss here. So once you do that, and then we have these reference measurement channel settings for uplink and downlink. So here you will set what is my MCS scheme and what is my throughput that is expected of for both downlink and uplink. Okay, so these three are the main parameters that you'll initially configure. But apart from that, again, this is a base station, so you have like tons of parameters that you can configure. And then in terms of authentication, so we use a Gemalto SIM, obviously, so we configure that to the exact SIM configuration settings. And then once all this is done, that's it. So you have 3 tabs here: measurement, signaling, and IP data. So you just go to signaling and see right now it's idle. And I have a device. which is my Galaxy Note 10 device here. So if you go to about phone, so it's Galaxy Note 10 plus 5G unlocked from Verizon that can support both FR1 FTD bands and FR2, both the bands now. So I'm just going to do an airplane mode. Okay, and then you'll see the RRC messages transferred between the base station and the UE side, and then you see it in connected mode right now. Okay.
Quick question. So for getting the UE up, do you have a test SIM card in there?
Yeah, we do.
Okay.
We do. Yeah. So basically, I mean, you can use any kind of test SIM that you want, and you can let us know the K values or the OPC code, then we can key it here. So if you don't know what that is, then we'll probably use a user, and then we can probably get that information from you, and then you can load it here, and then you can still be able to connect. It's not a big thing.
Yeah. Okay.
Cool. Okay. So
and
sorry.
So we have some test SIMs here, but are the test SIMs different for 5G? Do we need new SIMs?
So for non-standalone mode, 5G does not care about any SIM because we still rely on LTE protocol for the initial call connection and for any voice calls.
I see. Okay, so any LTE SIM will do.
Yeah, it'll do. But for standalone mode, it's going to change, right? Because it's hardcore 5G next-gen core, and there is no LTE to fall back on. So that is when we would need new SIMs and SIM settings for 5G standalone. Okay. Cool. So once you see it in connected mode, you will see my IMSI, IMEI, what is my UE category, and all those kinds of information. And we have a tab called UE capability. So this is really good, which says that which band combinations and is it CA supported or is it CISO only, is it MIMO? So all these information may be listed here. So my UE category is only 4, 6, 9, and 11, and supported bands are these many bands here. Okay, so this window is really helpful, and you will see this only when you have the device in connected mode. Okay, all right. So the other thing I want to mention is we have a measurement report again based on the UE's transmit power and the output level that we set. So we have the RSRP measured based on the E-pre settings and based on the external loss, the pre-space loss, and everything included. So you see my RSRP is minus 70 dBm per hertz. Okay. All right. So again, so this is the LTE side of it, and then now you switch to 5G and our GUI here. Again, so here we have like tons of settings that you'll have to configure, and this is just to show you that how is my FR2 setup configured right now. So my slot 1 TRX1 is hooked up to a 39 gig converter, slot 2 TRX2 to a 28 gig converter here, and both are connected to port 1, which is my phi polarization. And these two are, again, obviously different signals, but both are set to my phi ports. Okay. In terms of settings, again, as you see the GUI, it's really similar to my LTE GUI. So you just go to general. So here you have like two options. So one is you can turn the call processing on, which is basically doing it in a signaling mode. But if you don't want to do it in a signaling mode, then you can turn it off, and then you can generate my NR waveforms if you want to do like a non-signaling kind of testing. So we have like a lot of different test houses who are trying to do this non-signaling testing for 5G modules, not for commercial devices. Obviously, you cannot do that on a commercial device today. But for any 5G new chipset modules that they're trying to test, then you can use this in non-signaling mode as well. Okay. So right now,
could you explain what the signaling mode and non-signaling mode difference?
So if you look at the option right now, right, it's selected to ENDC, right? So ENDC is basically dual connectivity mode, so where you would need like both LTE and NR
I see.
connections and configurations at the same time, because we rely on end-to-end a protocol stack for both LTE and NR while doing the signaling activity. But for non-signaling what it means is, so we'll generate an NR signal based on a waveform that we create. Again, this waveform is generated like based on the 3GPP settings for a, say for a specific RMC and for MCS and stuff. So we generate that waveform and we transmit that out of the MT8000A call box. Okay, so that is our part. But from the UE side or from the chipset side, they'll have to make sure that their chipset is in a specific state, which they call as a test state or which is a non-signaling state, which can receive these waveforms and then do those TX and RX measurements.
Got it. So for MAC layer throughput testing, we need signaling mode.
Yeah, that's right. Yes.
Got it.
Okay. So I think that's what you see here. So there is none is non-signaling, and you have this ENDC mode here. So NR dual connectivity mode here. Okay. Okay. And then on top of that, there's a lot of different parameters, but so we have like a certain set of specs and parameters that we got from the handset manufacturing guys and also with the chipset manufacturing guys that is suited only for that particular device. So the same parameters won't work for my OnePlus or my LG device. Okay. So we need to make sure that we have all these settings properly configured for that particular device. So in terms of the frequency and the bandwidth settings. So here, of course, TDD is only supported for millimeter wave, and then the subcarrier spacing today, like you can go up to 240 kilohertz, but again, we don't have any commercial devices that can do that today. So we support only 120 kilohertz for this particular scenario, but we have an added option where if you want to test like more higher SES subcarrier spacing, then you can do that too. Channel bandwidth right now it's 100. That's what this device supports. SISO, it doesn't support MIMO. So again, if you have a MIMO device, then you can obviously go and configure this because 2x2 MIMO is again an added option. So if you have that license, then you'll see this option here, 2x2 MIMO. Okay.
One question. So for 400 megahertz, the 4 times the 100 megahertz, how do we do that?
So that needs to be on a MIMO setting. So you would need a minimum of 2x2 MIMO, and then you'll have an option of setting the bandwidth up to 400 or 800 meg, depending upon the hardware config. For SISO, it's only 100 meg.
Okay, so if we go MIMO, then each MIMO can do 400. So that means each RF connector can output 400 megahertz?
Yeah, that's right. Yes.
Got it. Got it.
Okay. Okay, and then we have like a TDD configuration here. So again, it's like, so we have like different time slots, right? On which each time slot you have your downlink PTRS or any kind of channel that transmits, and then you have your uplink slot. So based on the 3GPP settings, you'll probably have to set all these information here. And again, a scheduling type, we have static, which is just the fixed DCI. There is no DCI specification for any of these downlink and uplink slots. If you want to customize it, then you can select user define and then you can manually configure it. So you have that option too. Like an LTE, again, signal wise, channel coding is your reference measurement channel. And again, you go to uplink RMC setting, you can set your MCS like to 16 or 5. So let's just do QPSK for now on downlink and uplink, and then I'll change the MCS later on while it's in connected state. Okay. So once you have this configured, then you just go to frequency. So I'm setting it to band 260, which is my 39 gig. You see here it's 38.499. So both TDD, so downlink and uplink on the same frequency. And my level is going to be much lower because of the output loss. Okay, so right now, I mean, so when you're trying to do an OTA kind of measurement, there is no way you can have an accurate path loss settings or path loss measurements. So you'll have to like play around with it, make sure you know what is the gain of my antenna, what is the free space loss, and what is my cable or connector loss. So based on that, so we just try to set a fixed path loss, and once we have it connected, then we can actually do the actual path loss measurements to an accuracy level. Okay, so
this
right
output
now
level is output of the converter box.
The converter, yes, that's right.
Okay.
Okay. So this level, as you can see, it can go like all the way to 0 to minus 120, but right now you're seeing it to minus 43, and the reason being is because of my path loss. So I go to slot 1. I have my output level on and off. So here you can enable if the signal is transmitting or not. You can shut down the signal, or you can transmit the signal using this option here. Okay, and my external loss is on, and I'm actually setting it to 48 dB on both ports. Again, port 2 is not used, but still port 1 downlink and uplink, I'm setting it to 48 dB. And this is based on my calculation, what I did for the current setup that I had. Okay. In terms of the connection mode, so here you have the option. So you can actually select if you're trying to test my slot 1 or slot 2. Okay, so if you want to do 28 gig, then I select slot 2, but I'm doing 39, so selecting slot 1, and make sure you have the right TRX port. So I have a connection on TRX1, but if you were trying to use TRX2, then you'll have to select it here. Okay, so this is one of the main settings that you want to configure. So in terms of physical channel and again call processing, there is a lot of settings, as I said. But the main thing is like just make sure you have the right parameters that we know that is working for that particular device. So say for example the number of SSBs, right? So I'm just transmitting only one block here now, but again you can go up to like 64 blocks for millimeter wave. But I'm just trying to make sure I just transmit this SSB and the UE is able to decode it, and then I'm able to do my TX and RX measurements. That's all I'm trying to do here. Okay. So again, like there's all these PDCCH and PDSCH, and there's also for PUCCH and for PUSCH measurements. So all these channel information can be configured here. On top of that, we have a new settings for channel state information reference signal. So again, this is typically used for beamforming. If you want to generate like more than 8 or 16 beams, then you can have this configuration enabled. And then you have your PRACH power. It's similar to LTE. Nothing's changed here. Okay, except that my subcarrier spacing is going to be much narrower. Okay, all right. So once we have all this configured, and again, you don't have to do anything with call processing because 5G does not involve anything with voice. And then you go to TX measurements. So you just have to make sure which TRX port you're trying to measure. So I'm selecting TRX1, and there's a lot of other configurations for TX smoothness of the measurement. So if you want to do a pre-phase phase tracking, that's my PTRS channel, and you have my UE power class. So this device supports only UE power class 3, but we have like certain devices that can do 2 or 1. Okay, so based on that, you'll have to adjust all these settings here. Apart from that, again, since this is millimeter wave OTA, you can also do TRP and TIS testing, provided if you use Anritsu's own chamber, not the shield box. So Anritsu has their own direct far field chamber and Qatar chamber, specifically used for analyzing the antenna's performance and doing like certain testing, like beam forming and then beam width calculation. So for those kinds of measurements, then you can use your TRP settings. If you want to do a full suite for both phi and theta, and then how do you want to configure, you can change everything here. Okay, and then similarly for RX measurements throughput, this is your MAC throughput. So you can either send like n number of frames or n number of transport blocks. This is my TBS data. Okay, so you can configure that, and if you have a chamber for doing OTA measurements, then you can do TIS and you can do TIS CDF measurements. Okay, so right now, so we just do a simple static EARP measurements. So I have the configuration, and let's see if I'm able to attach. So right now, once I hit start, you see it says connected in NSA mode, right? So the logs here will show you what exactly happened here. So until this point, okay, so until this point, the LTE signal, the RRCD config complete is for the LTE signal. So once I click start on the 5G NR GUI, you see something called as an RRC reconfig SEG add. SEG is secondary cell group add. Okay, so the 5G GUI is actually talking to my LTE anchor saying that, okay, I have an NR frequency cell, which is on band 260, that I'm trying to add for that particular band combination on LTE, which is band 2. Okay, so either you will see a successful complete for that particular SEG add message, or you'll see an SEG sync failure. So if you see a failure that is something to do with a parameter mismatch or something to do with power settings, something to do with CQI, the signal measurements. Sorry.
Got it.
Got it. Okay. All right. So yeah. So again, this is really this again. So I mean, at the initial stages while working with Qualcomm, this was we actually had a tough time like making sure to make this work and stuff. But now it's a really stable product, so you can have any commercial devices connected, and then you can just run your measurements like just open the box. So okay. Okay, so in terms of measurement, so right now what I have is if you go to fundamental measurement, I have like these measurement items. Okay, so again, these are all based on my 3GPP specs. So I have my UE's maximum output power, my power control tolerance, occupied bandwidth, spectrum emission mask, adjacent channel power, and then my modulation schemes, obviously your constellation and then magnitude. Okay. So this device went to sleep mode. I'll just put it back to connected mode.
Are you giving these as templates also with the GUI, or does he have to start from scratch making his own templates?
Templates in the sense like an automated scripts?
Yeah.
Yeah, we do. So we have an automation software where you can run these test scenarios in a single shot.
Okay, and that comes. Mm-hmm.
Yep. Or you can use the GUI manually to actually run all these test cases here. So it's up to you.
Okay.
Okay. So let me just quickly do a power measurement with throughput on. So I hit single. Okay. So now I see my power. So this is my TX power here. Okay. So 1.72 dBm is what I'm actually getting, or based on what the UE is transmitting. Again, as you know, like UE's transmit power, it actually fluctuates a lot. So the first thing that you would have to make sure that the input level is set at closer to what the UE is transmitting, because this is what the MT8000 is actually expecting, and we need to make sure this is within an official threshold that the box can handle, right? So I'm seeing the peak is like around 8 dBm, right? So I'm setting it to 10, which is pretty good. But if you're trying to set this to like at 20 or 30 dBm, then it's really hard for the call box to actually decode the signal from the UE side, and it's going to drop the call. So this is the first step that you will do once you have the device in connected mode. Okay. And then in terms of throughput, so again, I'm like sending like 1,000 blocks, transmitting blocks, and it's going to measure like the AX or the NAX based on the UE's response, and based on that, we actually measure our throughput rates for downlink and for uplink. Okay, so right now it's in MCS5, I believe. So let's change it to 16 QAM and see how it looks like.
So MacPlayer throughput is basically the MCS measurement, like the packet error rate and the MCS and computing.
Right. And also with the signal conditions, right? Like how strong is the signal, and do you have any AWG in there, and all those kinds of stuff. Yes, yeah.
Got it. So the device doesn't know anything about the throughput. So if we want to see the throughput number from the device, then
that is something you would have to use an external post-processing tool like QXTM. It's chipset dependent, right? So
got it. Or do the IP layer IPERF or something.
Right. That's right.
Got it.
Okay. All right. So I'll just stop this, and I'll just quickly proceed over to this window. I think this is one of the important window. So once you have your device in connected mode on NSA, you'll see the same thing that you saw on LTE side, right? You have an UE capability is the same thing here, which is going to list what or the frequency bands that it supports on the LTE side and the NR side, because the band combinations is really important on the NR side, because without a proper LTE band combo, there is no way you can make a successful NR attach for any commercial devices. So That is why we actually have this window which says MRDC band combination. This is for the dual connectivity band combo. So for each and every device has its own unique band combos. So the good thing is once you have it connected, you will have this list here. Okay, so these are all the band combinations that this Samsung device supports. So this is for NR and this is for LTE. It also includes your CA band combos. Okay, so my N60 here and band 2 on LTE. And if you scroll through, I have N61 and I can do band 13. And this is my CA. So I can do N60, so it's a 2 CA, and I can do band 4 with LTE. Okay, so this is a really useful information if you're trying to like test for a particular frequency and for a particular band combo. Okay. And then it's going to tell me, okay, if it supports 60 kilohertz, obviously it doesn't support that because this is FR2. So FR1 can go 30 and 60. And then supported millimeter wave bands is 260 and 261 only for this particular device. And you see the UE power class is 3 for both the bands. And then you'll see some devices that can do UE power class 1 and 2. Okay. Sorry. The one thing is I'll probably end call and then I'll enable the measurement report. Then I'll end call here to start call and then connect. So here you see, right? So this is my primary cell and it's going to report my RSRP similar to what the LTE window was showing. So my RSRP is like minus 73 dBm per 15 kilohertz. Okay, and this is my RSRQ. So now, if you go here, right? So based on the path loss settings that I set, so 48 dB of path loss, and I'm transmitting at maximum of minus 43 dBm, and I'm getting minus 73, which is the same as the EPRI that I'm setting. So if these two values align, then it means that you have the right path loss settings. Okay. So again, yeah, so it is a pretty strong signal here, minus 73 dBm. And then, yeah, you can keep decreasing it and then try to play around with it. In terms of the other measurements that I wanted to show you, I'll probably turn throughput off and go to fundamental mode. So I click single. And then it's going to tell me, okay, what am I measuring? I'm measuring my occupied bandwidth. So we configured to 100 meg. It's 94 meg, and then we have all those guard bands. So I think that actually comes to 100 meg. And then spectrum emission mask. So for a different frequency, lower and upper frequencies, and then your channel power, right? Adjacent channel power. For plus or minus 100 megahertz. And then in terms of modulation analysis, so this is going to tell me what is my EBM, what is my SEM, and then what is my carrier leakage, ACLR, and my IQ imbalance thing. So these are all, again, from 3GPP specs. So and all this software comes with the predefined spec limits. So if it says pass, then it passes the 3GPP actual specs defined. But you can also change the limits accordingly, and you can customize the limits. But nobody does that, but I'm just saying. So, okay. And then, so this is just the tabular view, and here you have all these graphs and reports. So it's just going to tell you, okay, what is my upper frequency, what is my occupied bandwidth in detail with the graph. My SEM, so it's below the threshold, so that's good. And then my spectral flatness is pretty good. And then constellation. Okay, so right now this is QPSK. So you see, again, the EVM is okay. It's 5.24, but for an OTA thing, it's still bad. So let's try to change the MCS index to 16. Try to do a 16 QAM, and you should see the constellation diagram getting updated here. So for 16 QAM, my carrier leakage is like much lower, and my IQ imbalance is like still in 100% range. Okay. So since we have changed it to 16 QAM, I think I'll do that to downlink aspect. Let's just do a throughput measurement. So if you look at the throughput, right? So now, since we have like a 16 QAM configuration, my throughput is like at 58 meg now for downlink, and for uplink it's 81 meg. So there's only 2 packets that was actually not received. Okay, and yeah, again, as you said, like, so those templates that you were talking about, so this is where you look for it. This is my power template. The on and off power, this is my SRS template here, and then your PRATCH, power control tolerance, and then your spectrum monitor. So you can actually look into that, and then you have all these other 3GPP test scenarios that you can just open and then just go into the details of this. Okay.